So good morning. Once again we continue with our discussion. Now we consider the next case, namely lambda 1 and lambda 2 are real and lambda 1 is less than 0, less than So let us take the in this case both lambda 1 and lambda 2 are real. Now you have the two solutions x1 t y1 t. This is given by a1 b1 e to the power x2 t y2 t given by a2 b2 all the earlier comments hold about a1 b1 and a2 b2. They are the eigen vectors associated with lambda 1 and lambda 2 respectively. They are linearly independent. Therefore, these two form a fundamental set of solutions. Now, our assumption is that lambda 1 is less than 0, lambda 2 lambda 1 is negative, lambda 2 is positive. They are naturally different. They are real and different. Now, you see that since lambda 1 is negative, you see that x1 t limit t tending to plus infinity limit t tending to plus infinity y1 t is also equal to 0. Okay, let us draw a diagram. So that is probably. So let this be the coordinate axis. This be the direction of a1 b1. And then this be the direction of a2 b2 eigenvectors. In fact, this whole thing is eigenspace associated. This is eigenspace associated with lambda 1. This is associated with the eigenspace lambda 2. I mean, they are characteristics. I mean, there are two characteristics. So 0, 0 is the equilibrium point, and these are two characteristics. And you see that since lambda 1 is negative, x1 t y1 t, so this is the path corresponding to this goes to 0, and here these two characteristics have the property that they go to 0, 0. Okay, whereas you see that this characteristic has the property, since it is associated with lambda 2 which is positive, you see that as t tends to plus infinity, this becomes unbounded. Okay, so or I can put it this way, as t tends to minus infinity, this goes to 0, x2 t. So what we have is this limit So the past history of the characteristic x2 y2 is that it originates from 0, 0 and then runs away, whereas the behavior of x1 y1 is that it comes from infinity and collapses to 0, 0. So this is the I have indicated by these directions. Now we can look at what happens to a general characteristic. So a general characteristic I can draw like this. Xt equal to, as before, it is C1 or C A1 e to the power lambda 1 t plus d A2 yt equal to, this is the general characteristic, C B1 this is the general characteristics. Okay. Now you immediately see that you cannot say that xt goes to 0 or yt goes to 0 unless, as t tends to infinity, unless you have d equal to 0. So if d is not equal to 0, then you cannot say anything about the limit of xt and yt. In fact, they become unbounded. Okay. If d is not equal to 0, in fact, goes to infinity. So when d equal to 0, it does. Okay. When d equal to 0, you are talking about this particular case. Your xt yt is essentially x1 y1. So that we have already looked at. Okay. So if d is not equal to 0, this is not. So you see that none of the characteristics really, I mean not none, except these two characteristics, no other characteristic ever enters or approaches 0, 0. All characteristics except the d equal to 0. Do not approach only two characteristics approach the point 0, 0. All other characteristics do not never go to 0, 0. Okay. And you can even work out the behavior of this as what happens as t tends to plus infinity, in which direction they will be moving away. So you can work out this. So you find out yt by xt, find limit t tends to plus infinity you can show that this is equal to A2, B2 by A2, assuming that D not equal to 0. What does this mean? This means that the path along which the particle escapes is always eventually along the direction of the vector A2, B2. Okay. So this is the direction along which all paths other than these two run away. But you can also see that limit t tend to minus infinity, where do they come from? Yt by xt, this is equal to what is it? B1 by A1. That is all characteristic start off at infinity along the direction A1, B1, and except this one, everything else will run away. So the path is something like this. You know that the characteristics cannot cross. Any characteristic in this region will remain there. So also here, so also here, so also here. I made this comment earlier. So what you have is that the picture is something like this. See, the characteristics would start in the direction A1, B1 and then turn around and just escape like this. So also you have this is the path of it, and you know all characteristics are having this behavior. And what happens here? Here also similar behavior is there. Follow this path. Now let me mark the rectilinear path with some other color so that it will be visible to you. See, these are the two paths that you have. The linear paths. These are the two linear paths. These are the linear paths. And all others are all the characteristics. So something that here goes like this. And you see that this is also the behavior. No, I think it has to be like this. Yeah, start from here. This is the final picture that emerges of the paths of the characteristics. Now this is what is called the saddle point. Now I think you would have seen the seat that is often fixed on the back of a horse. How does it look like? It's something like this. Something like this. This is what is called a saddle that is fixed on the back of a horse. what is the nature of the curvature of this particular saddle? You see that if your particle is moving along this direction, then it will just reach here. This is the equilibrium point, and anything that starts here will automatically slide down along this path, and this, I mean, this is very delicate. It's not a very stable path that you have. But on the other hand, if you start somewhere slightly here, then what happens? It will just go along this, but then it will run away along this direction. So also, and it is these kind of paths that you see here. Therefore, the behavior of this point is exactly like what you see on the back of a saddle. That is the equilibrium point. This equilibrium point is very unstable, and you see that these are the only paths on the back which comes there, but these paths are again unstable, so you run away along these paths. On any other path you run away. All the paths run away along these directions, these two directions, and you see the paths would originate along this. Okay, that's what you see here. Here you see that the unstable equilibrium point that you see, the unstable path that actually approaches 0, 0 is this. All other paths. So for instance, if a particle is moving along this direction and for some reason it is perturbed, what will happen? It will just run away. Okay. So this is very unstable. That's why I said it's very unstable, like this path. If you roll a marble down, see, it's very difficult to get it reaching here, because if by some reason it is perturbed from that path, it will just run away. This is what is called a saddle point. Now you would have seen, I mean, you can actually look at the equation of this surface and just go into what is called, I don't know, there are some mathematical softwares where you can see this, the description or the equation of the surface that determines the saddle point. Okay, right. It's a very nice geometry that comes out. But this is an unstable equilibrium point. This is an equilibrium point, all right, but unstable. Okay, so this is what is called a saddle point. Now these computations you do. Okay, right, and if you also check whether my statements make some, are there some mistakes related to that. So let me now take up the case 2. Okay, let me make a comment before that. Comment is this. In this particular book by Hurevich, what he does is this. He transforms the equation into because wherever you can diagonalize it, what you can do is you can write it in this particular form. So this is the equation. This is the equation that you have. Now wherever you can diagonalize this, what he does is, how do we diagonalize it? In the situations that we have already considered, we are assuming the eigenvalues are real and distinct. Therefore, you have the corresponding eigenvectors a1, b1 and a2, b2 associated with lambda 1 and lambda 2 respectively, giving an ordered basis. You choose that as the ordered basis, and then what you get, you can transform this equation into and this transformation does not alter the behavior of the equilibrium point. 0, 0 will remain the equilibrium point in this transformed equation also. But what happens is you are introducing a new coordinate system in which this particular matrix is diagonal. The advantage of working with this is that, you see, in the new coordinate system, this a1, b1, a2, b2 will be something like this. Okay, so this is your, so corresponding to lambda 1, what is the eigenvector that you have? 1, 0. So corresponding to lambda 1, you have got E1. Corresponding to lambda 2, the eigenvector is E2. So they are it actually simplifies the calculations. In fact, in the XY space, capital XY space, that is the transformed space, you see that these are the rectilinear characteristics, that is spanned by, this is E1, this is E2. E1 is equal to 1, 0, this is 0, 1. Okay. Then what is the scenario that you had earlier? You see, when both lambda 1 and lambda 2 were negative, you see that these were always like this, and all paths had been in this way. See, all characteristics enter along, I think what was the direction in which it enters? It is along lambda 2 or lambda 1. So let me check. D by C. Okay. D by C is 0, 1. Okay. So all characteristics enter like this. This is the scenario that we have considered earlier. Now, when both lambda 1 and lambda 2 are positive, what happens is you end up with the same picture, but the direction of the arrows reversed. Okay, so this is the first case. The saddle point case, in that situation is this. You have got lambda 1, lambda 1 negative, lambda 2 positive. So in this case, of course, the corresponding to lambda 1, this is 1, 0, corresponding to lambda 2, 0, 1 is the eigenvectors in the transformed equation. Okay. Then what you have is that the following, that corresponding to, this is corresponding to lambda 2. Okay. So corresponding to lambda 1, you have this direction, this characteristics, and these characteristics have this direction. And then you see that the curvature around, that is the characteristics all start along this and then run away. This is the saddle point that you get. This is the characteristics that you have. This is again 0, 0 is a saddle point. The other one is what is called a nodal point. In both the cases. Okay, the only thing is the direction will change, that's all. Okay, so this is the scenario. Now we take up what is called the degenerate nodal points. That is the case 2. The degenerate nodal points is again the following. Okay, you have this case 2. The eigenvalues are here. Multiplicity 2. In this situation, you see, lambda is the only root of the characteristic polynomial. So then what you have is this. For that value, we look at the rank of A minus lambda, B, C, D minus lambda. Lambda is see, you know that for the choice of lambda, you see this, the determinant of this is equal to 0. And that can happen. And if that is the case, two things can happen. The dimension, or what you call the rank of this one, is certainly less than 2. So what are the possibilities? The possibilities are either this is equal to 0 or 1. Both the possibilities are there. Okay. What happens if it is 0? If it is 0, let us take the case where rank of what does this mean? This means, you see that both these rows are 0, 0 or both the columns are 0, 0. When is that possible? Because this is 0 provided lambda is equal to a, but lambda is the same as in both the cases. Lambda is also equal to d, so a should be equal to d. Lambda. And of course b equal to 0, c equal to 0. This is the situation, specific situation. So if you are what is it, if the rank of okay, this implies right, and no other case it will happen, otherwise it will become, the rank will become 1 even if these are the eigenvalues. Okay, so this is what you have. Therefore, what is the scenario that you have? The equations would be reduced to simply dx by dt equal to a equal to lambda, so it is to be lambda x b is 0 and dy by dt integrate this. What are the solutions of this? Okay, so you see that xt equal to, you can, because they separate, you can integrate it. Xt is equal to c1 times or c times e to the power lambda t, and yt equal to d times e to the power lambda t. So the solution is essentially of the form c e to the power lambda t d e to the power lambda t, or this is of the form C and D you can choose depending on some initial condition, and therefore this takes care of all the possible characteristics by taking different values for C and T. Okay, and what does this mean? X is equal to C e to the power lambda t, y is equal to D e to the power lambda t. This means you have y is equal to kx. Okay, y equal to kx, or something like, you see that dx minus cy equal to 0. If you eliminate t between them, dx minus cy equal to 0, or you get all sorts of lines of this form. This is just not very exciting because not of much interest anyway. If you draw the characteristic curves, they are going to be all radial lines. x equal to ky or y equal to kx. All radial lines will come. Okay. Now you see that if lambda is positive or lambda is negative, then you see that the directions along all the paths are, they enter the 0, 0. Okay. If so, the direction on the characteristics eventually any particle anywhere will take a radial route and just collapse to the equilibrium point 0, 0. But if lambda is positive, then the direction reverses. Or what happens is that your equilibrium point becomes a source and things will start running away from there along the radial direction. Okay. So the arrows will get reversed in the second scenario, namely when lambda is positive. So this is what is called a degenerate. This is a degenerate. Corresponding to the case where this is equal to 0. This is the condition that we have looked at. That is rank of, so eigenvalues are lambda with multiplicity, algebraic multiplicity 2, and then you see that this is the scenario that you have, and this can happen only when A is equal to D and B and C are 0. In that case, this is the picture that emerges. A very simple situation. Now we look at the more general situation. So this is the case A. Okay. This is equal to 1. That means at least one of the rows, what you have is that two rows are there, the row vectors are now linearly dependent, but they are not identically 0 vectors. This is the situation that you have. Right. So let us work it out. This is a more general scenario. Now you see that when this happens, lambda is a multiple eigenvalue but the eigenspace is of dimension 1. So let us assume that the eigenspace is given by, so let lambda. Then you have immediately a solution. Lambda t. So that is one solution. And you have seen that the second linearly independent solution then the second linearly independent solution is of the form is given by the same A that appears there, AT plus C where A and B are exactly the same thing that appears here, and then CD with a certain relation connecting them. Okay, so you check whether determine this. Now A and B are the eigenvectors associated with lambda, but CD is not an eigenvector related to, but you have the property that CD is a vector for which A square, or when you take the matrix A minus lambda B C minus lambda D, when you square it, so that nullifies CD. This you would have already analyzed. Okay, right. Therefore, let us take the case now. Lambda is assumed to be less than 0. Lambda greater than 0, it's very easy to analyze. Now you see that both these vectors, they are linearly independent. Both these, so they span the solution space. Okay, so you have, consider the case this is 0, then a general solution xt is of the form what you call A, B, C, D. Now I'll write some number. Oh, okay. Let me write some other than ABCD. So I take, E is a number, E times where E and D are, E and F are Now, one thing that you observe is that the following. So, what is this is xt by t. Yeah. So, xt equal to E you can replace by that. Now find out this limit t tending to plus infinity yt by xt, assuming lambda is negative. Okay, this you can show that this is equal to b by t. Similarly, in this case, limit t tending to minus infinity of this is also equal to b by t. So you see that all the characteristics originate along the direction b by a and enters the equilibrium point along the direction b by a. So that is the scenario that you have. So what do we have? Let us draw the picture. Here you need little bit of delicate analysis to two scenarios can emerge. I'll just find out. So the pictures are this is the picture that you have. This is the suppose this is the direction AB. This is the equilibrium point. Now what happens? See, this is the direction along this rectilinear characteristics. Other characteristics are they start along AB and then enter along AB. They start off along AB but then enters 0 0 along AB. Here also it happens. Okay. Now you might ask why like this? Can you not draw like this? The other scenario is equally possible, namely this is equally possible. But what distinguishes the two? Let us analyze this. So there are two possibilities. Either you could have a picture like this or you could have a picture like this. But which one you get? Let us analyze this. To analyze this, what is the problem? The problem is this: dx by dt yeah. Okay, tell me.
Here, what will be the second vector? AT plus T and BT plus T?
This one. This is AB and CD. C and D, see, you would have seen how you write down the second solution. But A and B will be the eigenvectors. They will be the corresponding the entries of the eigenvector. C and D will be, some vector for which you see that the square of the matrix will be making it vanish. It is not the eigenvector.
That vector will not play any role in drawing the...
No. It has no role at all. You explicitly work out this limit. Only this eigenvector will have a role. They all start off along this eigenvector, the direction of the eigenvector, also enter along the direction of the eigenvector. The other one has no role except in determining the actual shape of the characteristic curve. Is that all right? Okay, right. So let me just now take, there are two possibilities here. Both are equally possible, but how do you distinguish the two? For that you look at these two equations. Okay, and then look at, see, this is the solution of this is what is called an xt by t is a characteristic. Okay, so let me see what happens to dx by dt. Okay, I evaluate along 0, 1. That is at this point. At 0, 1, what is this going to be? X is 0, y is 1, b. Okay? Now what does this say? Suppose b is positive. B is positive means what? X is increasing at the point, X is increasing at the point 0, 1 if B is positive. No? And that indicates that the X coordinate increases means the characteristic is crossing this line. See, the characteristic crosses this point 0, 1 in this direction. So when B is positive, you are going to get this picture. The second scenario comes. But suppose B is negative. Then what happens? Dx by dt equal to B, at 0, 1 is B, and you get x decreasing. X decreasing means what? You are moving in this direction. In this direction. That means you cross this axis, y axis along this. So you can do this analysis by studying the behavior of dx by dt or dy by dt along the x-axis or y-axis. If you are looking at dx by dt, then do it on the y-axis. If you are working with the dx by dt, then you do it on the x-axis. Okay? Right? Because how y changes, along the x-axis you will be studying how y changes. Y is increases means you are going from the fourth quadrant to the first quadrant, or from the third quadrant to second quadrant. Okay, so this is the way of analyzing it. Which figure suits? I mean, both these situations are possible. Okay, you see that there is no inconsistency. You can, as I said, you can analyze with two things, either with dx by dt or dy by dt. You see that under this condition, where you get this is what you call there is only one eigenvector corresponding to the eigenvalue lambda, then in that scenario you will see that you will get a consistent result, either if you use the analysis with the dx by dt or dy by dt, that you can see for yourself. Okay, do you understand? I will explain it out. Okay, so if you are working with the x-axis, then what happens? You are working with the x-axis, are you going from the first quadrant to fourth quadrant, or fourth quadrant to first quadrant? This is the analysis that we are trying to work with. Similarly here. Okay, so you take the point 1 0 and analyze dy by dt. dy by dt is at 1 0 is cx. So the sign of c is going to matter. Okay, and you can show that the sign of c and the sign of b work in a coherent fashion. You won't get a contradictory state once you make this assumption. You can do the analysis. So I leave it to you to work through the analysis. So this is called the degenerate nodal point. Now we pass on to the next case where you get complex eigenvalues, and that's very interesting. Okay, so what is the equation? The characteristic equation is this is the characteristic equation, which is given by the characteristic equation is lambda square minus a plus d this is the characteristic equation. I suppose I am right. You can quickly work out the determinant of this and then get it. Determinant of this matrix, or I can, instead of putting two bars, I can write here determinant of this matrix is equal to 0. That is this. Okay, when do you get non-real eigenvalues? You see that the discriminant is negative, that is b square minus 4ac is negative. So this quadratic equation non-real roots. Negative. Okay, so that when you write down the two roots, it is going to be minus of this, that is a plus d, plus or minus these are the roots, and this is complex if this is negative. So that's the condition that we have put. Okay, so the real part of the root is given by a plus d, and the imaginary part is given by the square root of this in that case. So this is the condition that we have. What does this mean? Let us simplify this. This gives you, this I can rewrite in the form a minus d whole square do you follow this? We just expand it, then you can rewrite this in this form. What does this say? This says, this implies whenever this, see, this has to be negative because this is anyway non-negative. Therefore, this has to be negative. So, BC is less than 0. So, B and C should have the opposite signs. That is the inference that you get immediately. B and C have opposite signs. Okay. So now we take up the various cases. So case 1. See, what can you say about the roots of this? See, let us take lambda 1 to be alpha plus I beta. Then lambda 2 is going to be the conjugate of that, where alpha and beta are real. Because the equation, the characteristic equation has real coefficients, now the roots are going to be like this. If alpha plus I beta is a root, then alpha minus I beta is also a root. Alpha is real and beta is also real. Now we take the first case. So the first case is where assume alpha equal to 0. If alpha equal to 0, then you see that lambda 1 minus I beta. Now you can write down the solutions. See, you have two linearly independent eigenvectors which are complex vectors from which you can actually get real eigenvectors. I mean real solutions of the problem. So you see that. So when do you get alpha equal to 0? As I said, this is the lambda plus or minus this one. So we are assuming this condition, therefore this is negative. Okay. Therefore you see that a plus d alpha is equal to a plus d, or alpha equal to 0 so your the matrix has to be A B C D. A D is equal to minus A. It has to be something like this. Okay. Now what you observe is that suppose A, B, these are now complex numbers, is the eigenvector associated with lambda 1, then this is what you have. The solution xt is going to be it's a complex solution. Let me write this a plus I b. No, let me use this a plus I b c plus I d e to the power what is x2 y2? X2 y2 this is again another complex valued function which is given by these are the two solutions. So if I write this as alpha plus I beta, then this is going to be alpha minus I beta. These are the solutions. Now from which you can write down two real solutions, and they take the form, what will be that? Let us work out this. So let me write this one, x1t y1t, this is equal to a plus ib into e to the power alpha t into e to the power, that is cos beta t this is real. So this is equal to, write down this. Write down this. If you write down this, what you get, and you get a cos beta t minus b b cos beta t plus a sin beta t. And this part, there will be corresponding a and b replaced by c and d respectively, and just the same thing. So this is c cos beta t minus d sin beta t d cos beta t. This is the solution that you have. Okay, and from this you can extract two real solutions. You don't have to consider the second case. You will end up with the same sort of functions. So what are the real solutions that you can have? You can have a real solution corresponding to this multiplied by e to the power alpha t, and this part multiplied by e to the power alpha t. Okay, two real solutions are there. So any general solution is a linear combination of these two solutions. Now we take the case where alpha is equal to 0. Then the solutions are, the two linearly independent solutions are, one is x1t equal to a cos beta t The second solution is x2t equal to a b cos beta t plus equal to d cos beta t So you have two sets of solutions now for the system. Okay. Now consider the first set. Right? Eliminate t between them. What do? You will be eliminating, you will be solving for cos beta t and sin beta t from these two equations, and then what one does is just use the trigonometric identity cos square beta t plus sin square beta t equal to 1. Okay, that would eliminate this. So it will, if you do that, what you end up with is something like this. I think you check this, dx minus by equal to So if I now replace this by capital X and capital Y, that means I am using a transformation, and go to the XY space, then what do I have? I get X is equal to a constant times cos t, Y is equal to the same constant times sin t. Okay, so I get x square plus y square, a circle, okay, with capital X and capital Y, right? On the other hand, in the XY space, it is going to be something like this. It will give you an ellipse. Similarly, you take the general thing, and then what happens is all these solutions become ellipses, concentric ellipses, because you know that no two ellipse can, these characteristics can intersect. So they are all periodic functions, right? So these are all periodic characteristics. So they are closed curves. None of them go to the equilibrium point. But you see that once you are on a particular orbit, you remain in that orbit. You never go away from there. Okay? So once you are closer to this, then you remain close to it. Therefore, this is a stable equilibrium point. And this is something like the solar system that you have. Okay? There are, orbits around the equilibrium point. That is the case where alpha is equal to 0. Okay? And they become elliptic curves in general. But if you use the transformation x equal to this, capital X equal to this, and y equal to this, then you end up with the maps of this into what are called concentric circles. Okay, so that's the equilibrium point that you have. I think I will stop this here. Thank you very much. Sorry for holding you back. Okay, is there any questions? Okay, fine. Thank you.